let's proceed on to the next chapter, which is really a miraculous, a very important discovery, I should say, not miraculous, that took place in the early 1800s, and that was that electric currents can produce magnetic fields. The discovery was attributed to Hans Ørsted in 1820. He was a Danish physicist, professor, and he discovered that electric currents produce magnetic fields in the course of doing a lecture demonstration to a bunch of beginning physics students at the University of Copenhagen. So probably the one and only time that a discovery of significance was made during a lecture, at least by the professor. Maybe some of the students do. Uh, but to sort of set the stage for what he discovered and how he did it, think of this as the tabletop up in front of a lecture. And he had been, Ørsted had been giving a demonstration with some bar magnets, and these are magnetic compasses that he was showing the effect of bar magnets on magnetic compasses. And then he turned to a demonstration with producing electric currents, and for some reason had not cleared off the table and had left a few of the compasses laying around the tabletop. And also, for some reason, he had a configuration in which the current was going up in this direction. Think of this as a hole drilled in the table and a wire, long wire that goes up through it that carries a current I. So it was a long, straight wire, probably much larger than one would normally deal with, and mainly because it was probably a lecture demonstration, and had this kind of unusual orientation that would probably not be the first way you would think about doing it. For some reason, it was. And what he discovered is that when the current was on, like I have here, that these compass needles aligned in different fashion than they usually would. Yeah? And that's look at from the top. So if I get on the top and look down on this current, so there's the wire current coming right out at me, and let's say I've got four of these compasses sort of scattered around equal distances on a circle of radius r, let's say, and that maybe this is the direction north. Well, ordinarily, if there was no current going through here, all of these compass needles would be pointing north, straight north. But immediately upon turning the current on, they would snap to this orientation. The one on the top would be going to the left, the one over here down, one over here up, and then the one at the bottom here looking down is going to the right. And he flipped the switch on and off several times and would find that they would always align north. Uh, and then when he flipped the switch back on again, they would line up in this fashion. So it was readily reproducible. He probably thought, well, something was wrong with his compasses, but he found out quickly that that wasn't the case. Well, the story goes is that when he saw this in lecture, he immediately stopped everything he was doing and ran back to his lab to begin investigating this phenomena, because he knew immediately that he had shown a connection in this lecture demonstration between currents and magnetic fields. Uh, and no record was given as to what happened to the students. I assume it dawned on them at some point that Ørsted wasn't coming back, at least not that day, and so they wandered out, class ending a little earlier than usual. What Ørsted found was, for these very, very long wires, so long he was somewhere near the center of them, that the field swirled about it in this fashion. Uh, and you can get that from a right-hand rule, and the rule is a little bit different than the usual right-hand rule. And this one, sometimes called right-hand rule number two, is to determine the direction that these magnetic fields will swirl about the current carrying wire, straight current carrying wire. Pretend like you grab the wire with your right hand and your thumb pointing in the direction the current's flowing, and then your fingers will naturally curl around the wire in the direction that the B field goes. Yeah. Well, a little more quantitative experimentation with it uh, Ørsted found the following. I'll put it in modern notation. It's a little easier, it turns out, for this particular case, for the magnetic field to be represented in terms of not Cartesian coordinates, but in terms of plane polar coordinates. Again, if I line my XY plane perpendicular to the tabletop up here, such that the current is, I'm looking down on the current, so that's the same as this picture. I just put this coordinate system. And then I go a distance r up here to this point and say what's the magnetic field at that point. Well, magnetic field is a vector. Ørsted knew that. And it points in that swirling direction in this direction here. But an easy way to represent that is the following, using not x and y to locate this point, but r and theta. So you don't use Cartesian coordinates, but you use the plane polar coordinates r and theta. You may not have seen unit vectors, but you can associate unit vectors with those. R hat is a unit vector that points away from the origin at the point in question in the direction of increasing r, so it's going to be r hat as a unit vector that points in that radially outward direction. And then theta hat is always at right angles to r, so, and it would be in the direction of increasing theta, so theta is increasing in this direction, and so it would be up in that direction. And if you use those coordinates, then the magnetic field is exactly in this theta hat direction. Well, doing some quantitative experimentation, one's able to find for this particular very long wire that the magnetic field that's produced and shown up here is given by an expression like this, at least in today's units that we use. It's kind of a strange law, at least to this point, because it's a 1 over r dependence of the magnetic field. And people were used to 1 over r squared, so that was the first thing that had to be overcome. Remember, 1 over r squared, the electric field falls of a point charge falls off like 1 over r squared. I is the current in amperes. R is the distance you are from the wire radially outward. So if you go here, you go radially away. If you're up here, you go radially outward, perpendicular to the wire. That's in meters. And then B in Teslas. And then one has a constant of proportionality, which in this case, in today's units, turns into mu naught over 2 pi. And mu naught is a fundamental constant in this presentation of the magnetic field. And in SI, rationalized MKS units, has the units 4 pi times 10 to the minus 7th, Tesla meter per ampere, if we're in the vacuum. That is given a name, and that's called the magnetic permeability of the vacuum, and air is close enough to that same value, so you could also call it the magnetic permeability of air. One can contrast this expression, and people did, because they were very familiar with Coulomb's law. And Coulomb's law, for a very, very small charge, or maybe a piece of the charge, infinitesimal amount of charge dq, produces an electric field dE that goes like 1 over r squared. And if you look at this expression up here, well, it doesn't fall off as 1 over the distance from the wire. There is some other similarities, though, in that the current is what produces the magnetic field, and so it's proportional to current, like charge is what produces this electric field. And there's a fundamental constant out front. Yeah. And the direction is kind of strange. It's not radially away, as one might think, but is in this theta hat direction. But the thing that bothered most people was the fact that this fell off as 1 over r squared, and this only is 1 over over r. And so immediately people began to look for what could we get that would be a more analogous formula for the magnetic field, more analogous to this Coulomb's law. And the people that discovered or developed that through a series of experiments was a couple of French physicists, Jean Biot and Félix Savart. And really didn't take them all that long to formulate it later in the same year that 1820 that Ørsted made his initial discovery. They read about his discovery and then began these series of experiments. Uh, what they looked at, and you got to realize that most current carrying wires are not straight, or at least not straight for very, very long distances. Ultimately, they have to be a closed circuit to come around on themselves. So at some point, they got to curve around. And so naturally, one is led to think, well, I could chop it up into small little infinitesimal straight line segments of length dl, and then one has a dl vector that points in the same. It's of length dl. There's that length of that little segment, but the direction of it is the direction along the wire in the same direction as the current's flowing, and the distance r away. So they thought of the current just in this little piece here, and then they went up to a point. They wanted to calculate the magnetic field, and they locate that from this piece of current that is producing the field by an r vector to the point where they want the field, and develop this expression here for the, at least in today's system of units, for the magnetic field that was produced there. It's a little more complicated, but in that it has a vector cross product here between dl vector and r hat, but it does have a 1 over r squared dependence. The stronger the current is, the stronger the magnetic field at this location is. The direction with the cross product here is the right direction that one would find. You can, in this case, it's downward. And usually you could either use a coordinate system, a Cartesian coordinate system to evaluate this, or you could take the magnitude of this knowing that it follows the right-hand rule for the direction downward. So if you take dl and crossed it into r hat, it's going to be perpendicular to both of those going downward. I'll say a little bit more about that here in a second. If you take the magnitude of this, it's going to be the magnitude of a bunch of quantities here, but the magnitude of dl is just dl. The magnitude of r hat, which is unit vector, is 1, and then r squared. And that theta, it turns out, is the angle between dl vector and capital R vector in the plane that they form. Any two vectors, as long as they're not collinear, will define a plane. And so this is the plane that's determined by dl vector and r vector, that both of dl vector and r vector lie in this plane. So the Biot-Savart law is assuming that r vector here, if you look at dl vector cross r vector, that's going to give me a dB that's perpendicular to this plane. And since both r and dl lie in that plane, it'll be perpendicular to them. So perpendicular to both dl vector and r hat, b vector is. The angle is the smaller angle from the direction of dl to the direction that r is pointing in that plane. So you can take this magnitude and then use the right-hand rule to determine the magnetic field that's produced, dB, that's produced at this point over here by this infinitesimal amount of current, IDL vector. That's the Biot-Savart law in vector form or in magnitude with the right-hand rule in the form above. Named after Jean Biot, and Felix Savart. Biot and Felix Savart. There is an analogy between the two, and is worth pointing out, in that dE vector you can think of as produced by this amount of charge dQ, as this familiar Coulomb's law form. Here's the Biot-Savart law. You've got a constant proportionality here that depend really on the units that you're in. They both fall off as 1 over r squared for infinitesimal charges, small charges, and infinitesimal lengths of wire that are carrying current I. So the thing that corresponds most directly to dq over here is I dl vector, and they both have an r hat in them, but it's not just a scalar multiplication of a scalar times a vector, but is a cross product, a vector product between the two. Now, for the Biot-Savart law, it has not only the complications of the dl vector and r hat, but also the fact that you generally always have to integrate. So it's one of those laws that ultimately one has to perform an integration over all the current that's in the wire segment even of this factor. So just sum all these up, and that's a continuous sum.